Friday Transportation Seminar at Portland State University. My name is Chris Monsieur. I'm a faculty member in the Civil and Environmental Engineering Department. And together with my colleagues, we co-organized this weekly Friday Transportation Seminar. We're very pleased today to have Jason Ideker from our sister OTREC institution, Oregon State University, to present today on sustainability of concrete for infrastructure. So with that, I'll turn it over to Jason. Welcome.
Thank you very much. Appreciate that. Well, first of all, I'm kind of present fairly informally, so if you have any questions, something that's not clear, just feel free to interrupt me. I'm going to be talking a lot about concrete. My background is that I'm a concrete materials expert, both early age properties, so any concerns with early age cracking risk and early age volume change, all the way to long-term performance and long-term durability. So you'll see a lot of those themes kind of coming out through the talk today. So just kind of an overview, I'll give you a little bit of background about the research that we have going on at Oregon State, tell you a little bit about the classes that I teach. Some of you may be interested in some of those, and we can talk about ways that we can maybe make some of that happen. We'll also talk specifically about sustainability and what the link to durability is when we're talking about concrete for transportation infrastructure. And we'll talk a lot about some of the main degradation mechanisms that can limit concrete durability and concrete sustainability, all in the context of transportation infrastructure. Probably most importantly, we'll talk about what we can do about it. And I'll wrap up with some perspectives at the end. So I'm not going to give you a whole lot of details here, but basically the research emphasis that we have for our research group at Oregon State is developing and augmenting new and existing materials for engineering applications. We have a pretty big focus on test methods so that we make sure that the accelerated laboratory tests that we do really capture the field performance of structures in the long term. And that ties in a lot with the focus on long-term durability of cement-based materials. One of the main reactions and main areas that we study is alkali-silica reaction, so I'll be talking a good bit about that today because it really affects a lot of our transportation infrastructure and civil engineering infrastructure in general. Just to give you an idea, we have pretty varied research sponsors. The U.S. Navy sponsors a project related to fly ash usage in concrete. We also have two projects going on with the Oregon Department of Transportation really related to their high-performance concrete bridge decks. The Northwest Transportation Consortium is funding a project looking at climate change impacts and what that can do to infrastructure in the Pacific Northwest and Alaska, two very different climates but very important. And then we have a project that is in phase 2 that's sponsored by OTREC looking at the durability assessment of recycled concrete aggregates, and we'll talk about that a little bit in this project also, or in this talk also. I teach 3 courses at Oregon State. I put them in order now. So fall term, I teach an advanced concrete materials class to graduate students, but it's also open to upper level undergraduate students. The main 2 things we focus on there are development of concrete microstructure and durability, and really making the link between microstructure performance and microstructural development and what the long-term performance of the concrete is. I also teach a fairly new class. I've taught it once. Student in here, Christy's already had that class when she was an undergraduate at Oregon State, but it's focusing on green building materials, and it's taught at the undergrad and graduate level. And then in the spring, I teach our junior level civil and construction engineering materials class. About 90 students in that class, and it's a lab section course also. So we cover everything from aggregates to asphalt, concrete, wood, and steel. So when we start to talk about sustainability and the link to durability, somewhat I think the two terms are a little bit interchangeable, but we can't really be building and developing sustainable structures if we're not taking into effect what the long-term performance is going to be and what the ultimate durability is going to be. And a lot of that really comes down to ensuring long-term performance. What we're talking about is specifically long-term performance of the concrete. Doing life cycle analysis is something that's very important, and taking a systems approach. And so a lot of times it's not just one particular mechanism that can limit the long-term performance of our transportation infrastructure, but it's a lot of different factors coming together to potentially limit what the long-term performance is going to be. I mentioned here that long-term planning, we all know, is crucial, but it's often avoided when we deal with lowest cost bid for construction projects. And that gets into that bottom thing, and that's probably the most important, are the dollar signs, and it's really all related to economy. I really like this slide from the American Society of Civil Engineers. It gives us an idea of the scope and extent of the infrastructure problem that we have in the U.S. This kind of shows on the left-hand side where we were at in terms of the report card from 2005. The most recent report card that came out was in 2009, and we actually degraded down to a D- in the roads category, and our overall infrastructure grade stayed at a D. I think the interesting part here is that it's what's estimated as a $2.2 trillion investment over a 5-year period would be needed to bring the infrastructure up to a level that's just satisfactory, just to a level that meets the demands that we currently have. I think another thing that's really important to highlight here is that a lot of times we think about new construction, but for most developed countries, about 40 to 50% of their construction budget is all dealing with repair and rehabilitation. And the reason why that is so important, of course, our new construction has to be durable, has to be long-lasting. But one of the biggest things here is that for existing structures in need of repair, you don't want to come back and repair the repair. Yet we tend to do this time and time again. So the repair materials that we're using, and it's not just the materials, but the way in which we conduct the repairs and how we actually do the repair process and treat the materials when they get placed into service can really limit how effective those repairs are. So I think I just put a side note down here at the bottom to say that any new materials and any repair strategies that we use really have to exceed the performance of the current materials that they're replacing. Okay, so let's talk a little bit about cement and concrete. Concrete is the most widely used building material in the entire world. The only thing consumed in greater quantity on the planet is water. So this is a pretty significant thing if you kind of try to wrap your head around that. If it's difficult to wrap your head around all these numbers, this is a picture of me sitting on a concrete cube in Switzerland at one of our partner institutes. This is a 1 cubic meter block of concrete. And for every single person on the planet, every single year, that is how much concrete is produced, every single year. Gives you a bit of an idea of how much concrete we're producing. And then at the very bottom, shows you for about 1 cubic meter of concrete, so that amount of concrete, about 0.2 tons of carbon dioxide is produced. So what that boils down to is that the cement and concrete industry is responsible for about 5 to 7% of the world's output of carbon dioxide. So that's one of the reasons that you see so much emphasis being placed on reducing the carbon footprint of concrete. What is important about this number is that it doesn't really tell you the whole picture. That 5 to 7% is a worldwide average. In the US and in Canada and in Europe, we're responsible for about 1.2 to 1.5% of CO2 output. That's because we use very efficient kiln technologies. We recycle a lot of the hot gases that are coming out of the end of the cement kiln to preheat materials. So we reclaim a lot of that CO2 and put it right back into the materials so it stays in process a lot longer compared to very inefficient kiln technologies that are used in some developing countries. Those places may be responsible for 10, 15, and even 20% of the CO2 output. So certainly one of the biggest things that we can do to reduce the carbon footprint of concrete is to improve the kiln technologies and improve the manufacturing technologies that are being used throughout the world. Just as a point of reference, if you look at where the other major contributors are to CO2, if we think about commercial buildings, in the US, we're responsible for about 30 to 40% of the CO2 output from buildings. So certainly the concrete industry has a kind of a black mark for its contribution to CO2, but there are other industries and other areas that also produce a lot of CO2. So we're going to talk specifically kind of throughout the rest of this talk about how we can really reduce that CO2 footprint from concrete. Okay, so it's not all gloom and doom. There actually is some good news about concrete. Concrete does have a very low embodied energy compared to other building materials that could be used in its place. I'll show you a figure on the next slide to give you an idea about that very low embodied energy. We can also use concrete very effectively to make highly efficient structures. So the thermal mass of concrete can be used to moderate temperature fluctuations. It can be used for active cooling and active heating as well. Also, the light colors that we have that are typically comprising concrete help to reflect heat and light, so they can help to reduce this urban heat island effect that we have in large cities. The other thing that's kind of great about concrete is that it's a very forgiving material. It can take on a lot of recycled materials. We can include a lot of recycled materials, byproducts from other industries, that actually improve the concrete properties. So they don't actually make it worse. In most cases, they actually make it better. I'm going to put a side note down there too that high-strength concrete and the use of high-strength concrete can actually reduce the amount of concrete that we need in structures. So if we can produce a higher strength concrete, also a higher durability concrete, we can increase the lifespan and the intended use of that, and we can also reduce the amount that's required. The other great thing is that concrete itself can be recycled into new construction materials, whether that's new concrete, asphalt, backfill, insulation, or put into raw feed even for producing new cement. So this is the figure that I kind of teased you about, but if you look at a relative energy requirement that goes into the construction of raw materials, basically extruded aluminum, plastics, and structural ceramics are the most energy intensive of the materials that we use. Then when you get down into steel and glass and concrete, we're getting down into lower embodied energy materials, with concrete being the lowest of those materials.
Where would wood fall on?
That's a good question. It definitely depends, but wood is going to fall somewhere in between the glass and concrete, and depending on where the wood is produced and how far it has to be transported, can be even less than concrete. The reason why why I didn't put wood on here is that wood is not a typical building material that we use for civil infrastructure type applications. But there's certainly a whole other arena of the market where wood is a much better option than a lot of these other materials. Certainly the residential housing market is one of the places that we mainly use wood also. That's a great question. Okay, so I've painted a good picture for concrete, but like everything, that's not exactly the whole picture. There are certainly things that can limit the long-term performance of concrete. And I've got two pictures here. These are actually pictures I took when I was in Chicago a couple of years ago. And this is probably, I haven't done any investigation on this, but this is probably related to corrosion and freeze-thaw attack due to the climate and the amount of de-icing salts and chemicals that are used in the Chicago area. But I've hit kind of the four main areas that can limit concrete's durability. Corrosion is the first one, so corrosion of reinforcing steel. It's the most widely, it's the widest form of attack that can limit concrete durability, the biggest cause of degradation worldwide. Alkali silica reaction is in there at second and probably a close tie with freeze-thaw attack. And then sulfate attack is the fourth one that can really limit concrete durability. I'm not going to get into a lot of details about this, but sulfate attack can either come from internal sources, from when you're actually mixing and placing the concrete initially, or it can come from external sources. So that could be a source of groundwater or a source of soil that has high levels of usually some sort of a sulfate salt in solution. So I'm going to spend a lot of the rest of the talk discussing alkali silica reaction. So we're going to discuss one of these main degradation mechanisms that can limit the long-term performance of concrete. So don't worry, we're not going to get into too much chemistry. This is the only slide you're going to see on a little bit of chemistry. But the idea here for alkali silica reaction is that everything we put into concrete initially can actually set up the parameters to have this form of attack somewhere down the line. So you see that you need three constituents. You need a source of reactive silica, and that's coming from the aggregates. Not all aggregates have reactive silica, but certain aggregate sources do have reactive silica in them. You also need alkalis. So put up there, sodium and potassium are our main alkaline earth metals that the Portland cement is supplying to the system. And then you need moisture. So for concrete in an interior like this, like these concrete columns, the floor that's below us, that's not going to be susceptible to ASR because there just isn't enough moisture available to drive the reaction. We typically need an internal relative humidity above about 80% to drive ASR. So the main places that we see ASR are in transportation infrastructure and concrete that's exposed to the environment. So dams, pavements, bridge columns, bridge decks, those are all typical places where we see ASR. And this is your little blip on chemistry. The reaction is occurring between the high pH that we have in concrete. So concrete pore solution is around 13.5 to 14, so very, very high pH, very much like Drano. And the hydroxyl ions that are in that pore solution attack these certain reactive phases in the silica. They liberate the silica into the pore solution. That silica then combines with the alkalis, the sodium and potassium that are coming from the cement to form this gel. And this gel has a high affinity for water. It's hygroscopic. It wants to pull water into it. As it does that, the gel expands. As it expands around the surface of aggregate and in microcracks in the aggregate, it actually creates enough tensile force, or can create enough tensile force, to actually break the concrete apart. So the outward manifestation that you get from alkali-silica reaction is an expansion. So you'll see a lot of the slides that I show later on, we're measuring expansion for concrete that we've either cast in the lab or we've taken from the field. And if that expansion is great enough, you get an outward manifestation of cracking on the structure. This just kind of shows you the idea of what's happening. You've got aggregate inside a cement paste, and this can happen to both fine and coarse aggregate in the Portland cement concrete. And as that gel around the aggregate and inside the aggregate expands, it can actually crack the concrete apart. When you crack the concrete apart, you're opening up a fast path for other aggressive agents to come in. An aggressive agent may be water, just water coming in to help drive the expansion in the reaction more. You also set up the propensity for increased corrosion, freeze-thaw attack, and sulfate attack. So certainly we want to do everything we can to limit cracking in concrete. So what happens if we have ASR actively going on in hardened concrete? There's kind of two approaches that we can use. We can either treat the symptoms or we can treat the causes. So you kind of see treating the symptoms on the left-hand side deals with filling cracks, trying to limit the amount of moisture that can come into the concrete. We can also provide external restraint, so carbon fiber reinforced polymers to provide the type of restraint around a bridge column that we would need to actually constrain the reaction from occurring, that outward expansion. We can also do stress relief, where we actually remove parts of the concrete. I know that may seem strange. Why would we want to remove part of the concrete? But keep that in mind. We'll talk about a structure where that's been done. You can also treat the causes, but this is the much more difficult portion of the reaction to control. So certainly drying the concrete out is one of the most effective ways that we can limit ASR. If we can get that internal relative humidity below 80%, we can really reduce the risk of ASR. And that can be done through sealants, through cladding, through closing off any internal drain pipes that may have cracks in them, and from really limiting the amount of water that the structure has access to. We can also use chemicals. We're going to talk a good bit about this over the next few slides. One of the main mitigation techniques for alkali-silica reaction in hardened concrete has been the use of lithium salts, lithium nitrate, lithium chloride, and lithium hydroxide. And we'll talk about whether that's effective or not in the next couple of slides. Probably one of the most effective ways that we have for mitigating ASR, as I mentioned, is to dry the concrete out. There's a material called a silane. You may also see this as a siloxane. It's basically either a water or alcohol-based material that you literally paint or spray onto the exterior surface of the concrete. And it really acts like a one-way mirror. So it allows moisture to leave the structure, but it does not allow moisture to come back in. So it takes time for the moisture to actually leave, and of course that depends on your relative humidity on the exterior of the concrete to be a driving force to pull the moisture away. But over time, you can effectively dry out a structure with these silane coatings. Obviously, as the structure gets larger, it's going to be more difficult to dry it out, so you may have to come back several times and reapply the silane coating, and you may have to epoxy inject and fill cracks that open up over time just from the reaction occurring. But if you can keep a maintenance plan where you're coming back every few years for 3 to 5 years with this silane type coating, you can effectively dry out most concrete structures to prevent ASR from happening. So I mentioned the use of lithium salts. This is a project that I was involved in when I was at the University of Texas working on my dissertation. And you can see a typical highway jersey barrier there, or a concrete divider. You can see the type of cracking actually that we get from ASR, that map cracking. And workers going along and applying this lithium nitrate solution to the surface of the concrete. And the manufacturer selling this said, a number of years ago, this was a very effective way to control and mitigate ASR. What they'd shown was that in the laboratory, if you took small specimens, submerged it in the lithium nitrate solution, you can pretty much arrest ASR from happening because the lithium is very easily able to absorb into a small specimen. It interferes with the structure of the gel and renders it non-expansive, so you end up stopping ASR. We had some concerns, though, about how effective that would be if you can't drive the lithium nitrate deep within the structure where all of this reaction is going on. So we also did some work with vacuum impregnation, where you basically apply a vacuum pressure to the top surface of the concrete and you pull the lithium across and you try to drive it in that way. So what I've showed here are two graphs. They're both showing the depth of penetration of lithium nitrate into the structures. So these are both from the Jersey barriers. This is in Leominster, Massachusetts, about an hour and a half outside of Boston. And the red dashed line shows you the concentration that we need to control the reaction, about 0.01% or 100 parts per million. And so what we did was we took cores on the concrete, we took them back to the lab, we profile ground them, and then you do acid digestion to see how much lithium is actually there. And what you can see is that in the topical application, you only get lithium down to about 2 millimeters. So if you think about 2 millimeters, it's about that big over the width of an entire one of these Jersey barriers that may be anywhere from 150 to 300 or 400 millimeters thick. And then you really just get down to background levels at depth. As a point of reference, 20 millimeters isn't even a full inch into the structure. If we look at vacuum impregnation, certainly a lot better in this case. We're getting it down to about 4 millimeters, but we're still not getting it into any appreciable depth in the concrete. So this was certainly of big concern to us, that we're not getting the lithium into the concrete that we really need to control the reaction. So we moved on to a second structure. This one is for a bridge just outside of Houston, Texas. You can see some really nice tall columns. And you see this kind of strange apparatus with plastic and wood set up on the outside. I'll get into that in a minute. A bit of background about this. This structure was constructed from about 1999 till 2002, opened in 2002, and it was made with recycled concrete aggregate. So at the time, a very sustainable concrete mixture using concrete that's been taken out of service, so it's not going to be landfilled. It's put into a new structure. The problem was that the concrete that was used to construct these, the recycled concrete, was undergoing active ASR. When it got put into a new structure, it got put in with more cement that's supplying alkalis. It's an outdoor structure, and so it drives the reaction even further. And they had cracking beginning in these columns within about 3 to 5 years. So one of the things that has come out of this is a research project that we now have at Oregon State looking at characterizing recycled concrete aggregate sources so that we can make sure we have the right testing methods in place to avoid this type of reaction from occurring in new concrete. As a side note, Texas has since banned the use of recycled concrete aggregate in new concrete, so that you can only use it as a non-structural fill material, or it's landfilled. So getting back to how we actually tried to mitigate ASR going on in this structure, we used a technique called electrochemical injection. This is a technique that's typically used to remove chlorides from concrete bridge decks. What you basically do is you set up a temporary anode on the outer surface of the concrete. That's what you see here that's behind kind of that plastic sheeting. You tie into the rebar by drilling into the concrete. So we drilled in in essence, made Swiss cheese out of the column, not to affect it structurally, but about every 2 feet, drilled in 2 feet of depth into the concrete so that we could tie into the interior rebar and use that as our cathode. And the idea is that we can basically drive lithium ions into the heart of the concrete, and we can draw out a complementary cation. So we would typically be drawing out calcium ions. This shows you a graph, again, represented in a slightly different way, a bar graph, the percentage that we would need in concrete for the lithium here on the y-axis, and the depth in millimeters. What this is showing is a range of depth, so 0 to 3 millimeters, 6 to 9 millimeters, and all the way up to a 48 to 51 millimeter depth. So that's getting up to about 2 inches into the interior of the concrete. The great thing about this is that we see that we can get lithium in. Lithium is this lighter purple or the far left bar line. We can get the lithium into the concrete very effectively and above the levels that we need to control the reaction. The problem, though, is that we're actually driving in sodium and potassium and concentrating them especially right near the surface of the rebar, about 2 inches in. So we're actually setting up the propensity to have more severe reaction right at the surface of the rebar. So this is, it was a very interesting finding. It was good for us to learn this because basically we don't have a way right now that we can effectively drive lithium into concrete structures. And I think a lot of what came out of this research project is that using a chemical admixture such as lithium nitrate really is not a viable option right now for controlling the reaction. We've still got a lot of things we need to work out. I mentioned, just wanted to show a few pictures here. One of the options we could use in addition to silanes, in addition to trying to dry the structure out, is to provide some sort of external confinement, either in the form of post-tensioning or in the form of carbon fiber reinforced polymers. I'll show you just a little bit of background on another structure that we've been involved with also. This is a bridge in Wetumpka, Alabama. It's over 80 years old now. One of the fascinating things about this bridge, you can see it's a beautiful reinforced concrete arch bridge. And you can see close-up of one of the arches. This is arch 4. So if you're looking back in this picture, the 4th arch back that you can see. It's the only arch in this structure that has ASR going on in it. We've done a lot of petrographic work where we've taken cores out of the structure. We've sent them off to a petrographer who can actually look at it under a microscope, characterize the aggregates. We've done a lot of work on it in the lab to look at expansion measurements and to look at cement contents. We can't really figure out yet why this is the only arch that has ASR going on, because the concrete and the exposure conditions and all the other arches is virtually identical. But we've been monitoring this bridge really for about the past 5 years, and it's still showing a significant upward trend in expansion. So one of the ways that we actually monitor is that we embed stainless steel pins or stainless steel gauge studs into surfaces of the concrete. They embed typically anywhere from 1 to 3 inches, depending on how thick the concrete element is. They have a very small machined point at the end, and we use a comparator, basically a very fancy ruler, to go in and do hand measurements on the structure. A lot of times for historic structures, they don't want you to actually drill into the concrete and embed strain gauges. They want something that's a little bit less invasive and not going to affect the historical appearance. So that's one of the things that we do in this case. And then I mentioned a few of the other techniques that we can use to determine what's going on inside the structure once we take cores out of it. So I'll just show you, here's a picture of one of the cores that came out of this bridge. This is a core from Arch 4. And what we do is we bring it back to the lab and we put it into a sodium hydroxide solution at elevated temperature to see if there's a case for residual expansion, to see if there's still enough reactive silica and enough alkali in the cement to drive the reaction further. And what we could see from a core from Arch 3 was a fairly moderate level of expansion up to about 0.1%. And then in Arch 4, we see a continued level of expansion all the way out to about 130 days, up to about 0.2% expansion. So what it's telling us is that the concrete in Arch 4 still has the propensity to expand, and we need to try and do something about it. And there is the potential for expansion in Arch 3 also. So we have monitoring set up so that we can see if that arch is going to start to expand on us as well. Just a few nice close-up pictures of the bridge. We've been monitoring this continually for the past 5 years. What they're actually going to go in and do in the springtime of next year is do some epoxy injection on the cracks from the top surface of the arches so that they can fill those cracks, bridge them, and try to prevent any additional moisture from coming in. And then they'll come back with the silane and coat the exterior surfaces of the concrete to try and dry the structure out. Two of my colleagues from the University of Texas actually were just in Alabama this past week, and they instrumented the arches with 48 relative humidity probes inside the concrete so that they can monitor how effective these different mitigation techniques are at really reducing that internal relative humidity. So this is just kind of a slide to show you the monitoring techniques, or at least I shouldn't say monitoring techniques, it should say what the repair techniques are on the left-hand side. And then some impacts on the historical integrity, the structural integrity, the durability, the effectiveness of that repair, and the cost, to just kind of give you an idea of a double green plus meaning excellent, all the way down to a double red minus being very poor. So, certainly a CFRP from a structural integrity and a durability standpoint is a very viable option, something that could work very well, but it's one of the more expensive options that we have. One of the other things we're not too sure about is the long-term effectiveness of carbon fiber reinforced polymers. So we're starting to look into that as well. So that just kind of gives you a rough hit list of how effective these different repair strategies are. Okay, so we've talked about hardened concrete. We've talked about some issues from ASR and hardened concrete. But what else can we do, especially what can we do for fresh concrete, and what can we do to avoid the reaction in fresh concrete? So I put up kind of a hit list. We've probably seen these for sustainable development, but minimizing our resources in concrete production, obviously ensuring long-term durability both through proper design and construction techniques, as well as material selection and materials characterization, and then changes to our manufacturing and construction processes. So I mentioned that concrete is a very forgiving material. We can put a lot of recycled materials into it, and it can take on a high recycled content. One of the main ways that we can improve the sustainability of concrete right now is increasing the use of supplementary cementing materials. So I won't talk about all these other areas, but when I say supplementary cementing materials, we're talking about materials like fly ash, ground granulated blast furnace slag, and silica fume. Those are all byproducts of other industries that would otherwise be landfilled, but we can put them into concrete in varying dosages, fly ash and slag being the most forgiving, and that we can put probably 30 to 60% of those materials and replace a portion of the Portland cement and actually end up with a better material and a better product because of that. This kind of says the same thing I just said. So let's look at fly ash as a potential example. So fly ash is a byproduct of the coal-burning power industry. Of course, we could sit here and debate, do we really need to be having coal burning as our main source of power, but that's a debate for another day. I think at least for the next 20 to 25 years, we're going to have coal-burning power around. We're going to be producing fly ash. And so rather than landfilling it, we should be looking at ways to put it into concrete to make the concrete a better material and to keep the fly ash out of landfills. I really like this graph. This comes from the American Coal Ash Association, and it shows the uses, the beneficial uses of coal combustion products for about a 40-year period, from 1966 up through 2007. And what you can see is that the percentage of coal combustion products that have been produced has steadily been increasing over that 40-year period. What hasn't really caught up is the beneficial use of these materials. So in 2007, about 42% was beneficially used in applications ranging from concrete to soil stabilization to gypsum wallboard, a lot of different applications for these coal combustion products. But what it tells you is about 58% of that material is being landfilled. Even though we're looking at percentages, if you look at the total tonnage production, because the amount has gone up so significantly, we're landfilling a lot more fly ash and a lot more of these coal combustion products. Looking a little bit more specifically, this gives you an idea for EPA Region 8, 9, and 10, which does include Oregon. It shows you the coal combustion product production in 2007. The large blue wedge there is the actual fly ash and tonnage produced. And then it goes to show how much for regions 8, 9, and 10 of that fly ash was actually used in beneficial applications. So one of the main things that we use it in this region is in concrete production, so putting that fly ash into concrete to make it a better material. There are some challenges to using fly ash. One of those is the alkali content of the fly ash itself. So even though you may be replacing a portion of the Portland cement, the alkali coming from the fly ash may exacerbate ASR concerns. We have a project with the Navy that's actually looking at better ways that we can characterize the fly ash to use it in concrete more effectively. Another thing is that certain specifications, like the ACI Structural Building Code, limits the amount of fly ash that you can use. They do this because of finishing issues and the concern with salt scaling. But there's certainly a lot of applications where we can use higher volumes of fly ash, and this is something that we're trying to change through ACI and through ASTM. So I don't want to bog you down too much in boring details. We'll show you a project that I think is pretty fascinating, where fly ash is actually going to be used very effectively. This is the Mactaquac Generation Station. This is a hydroelectric power plant in New Brunswick, Canada, so far on the eastern coast. It's in the Atlantic provinces of Canada. And you can even see from a fairly decent distance away, you can see the amount of cracking, you can see the staining in the structure and the efflorescence coming just from ASR. So this structure was built in about the late 1960s. About 1967 was when it was completed. Dams typically have a very long service life. So this dam had a service life of 150 years. What's unfortunate is that the testing methods that they used at the time to look at the potential reactivity for ASR in the aggregates weren't the best testing methods. They were using what they had available at the time, but it wasn't the best approach that we now know. So what happened was they had all the propensity set up to have ASR going on in this structure. They started to notice cracking, started to notice and they started to do monitoring about 10 to 15 years after the structure was built. What you see here is that the structure, because it's embedded in bedrock on either side, the only place that it can go from this expansion is to go up. And so it's grown by about 175 millimeters since the time that it was built. So that's about 7 inches of growth in a structure like this. What they've done to combat this is they've removed concrete, and they've cut concrete out of the dam every single year just to accommodate the massive amount of expansion. You can see in this lower picture here, that's actually one of the flexible couplings that they have in the piping inside the dam. And they have flexible couplings in everything throughout the dam just to accommodate the movement and the expansion going on. They spend about $6 to $7 million every single year on this dam just dealing with ASR and dealing with the expansion. Because it's restrained on the sides from the bedrock, of course it can go up, but there are also holes inside the dam where the penstocks are that carry the water from the head pond down through the turbines and down to the river below. So it can also impinge on those penstocks, taking them from a circular shape to an oval shape. So they have flexible couplings in the penstocks, and that's why they have to come in and remove concrete from this structure every single year. So again, about 450 millimeters of concrete has been cut out. What they do is they actually have a system set up with diamond wire, and they literally cut sections through the concrete. They literally remove concrete from the front all the way back to the very back end of the dam from top to bottom, and they're removing concrete every single year. It's a pretty massive undertaking for the management of this structure just to keep it in operation. It's the second largest power generating station in Atlantic Canada, so it provides a lot of power to the area. So I'm gonna skip over this and jump ahead. Yeah, sure.
So a question on that. What if they don't remove the material?
If they don't remove the material, basically what happens is the expansion going on would end up crushing the penstocks. It's going to end up causing the turbine blades to be impinged so much that the turbines can't actually spin and generate power. And they estimate if they stop doing everything, within about a 1 to 2 year period, the dam would not be functional anymore. So yeah. Of course.
You mentioned that the concrete is getting removed every year. Could you just tell us what methods they use to cut the concrete out, and whatever is happening, is it a safe method without causing any raveling of concrete or absorption of moisture and developing cracks, things like that?
Yeah, well, it's a very safe method. I mean, basically what they're doing is, maybe this picture isn't the best to show it, but the diamond wire that's up in that upper left-hand corner is literally sawing through the dam, coming from the face all the way to the back. Because there's so much structural weight there and there's so much expansion going on, as they cut through, the concrete literally just closes up right behind it. So they're basically only providing stress relief in the concrete. So the dam is a gravity structure. There's not any reinforcement in it. It's a very safe and effective method. And they don't just use it on this dam. There are a number of dams in the world where they use this technique very effectively. Sure. So the unfortunate part is that rather than the dam lasting 150 years, it's going to have to be completely reconstructed in 2025. So it's only going to meet about half of its design life. And because the dam is such a massive amount of concrete, they have to use the locally available materials that they quarry from the bedrock right there. So we've been involved with a lot of testing to take laboratory tests, these kind of small-scale laboratory tests, to determine what are the most effective mitigation options to control ASR occurring from these aggregates in the new dam that they're going to construct, again, in about 15 years from now. So we used outdoor exposure site testing to do this. We had an accelerated kind of environment at the University of Texas, being a very hot and humid environment. There's also an exposure site at the University of New Brunswick, which is about 20 miles from where this dam is, so it can give us certainly a much more realistic exposure condition. We also had blocks that are the same size literally inside the dam, so inside the Mactaquac generation station, and they've been there for about 10 years now, so that we can monitor the effectiveness of different mitigation techniques. So I'm just trying to give you a little bit of an overview, but this graph basically shows what the expansion is for the completely untreated aggregate. So if they were to use this aggregate without any mitigation option, the bar graphs that are in white are the controls, or without any sort of mitigation. And what you can see is that you really need upwards of about 30% of fly ash replacing the Portland cement to control the expansion of this aggregate. But this wasn't really enough for the politics that are all behind this construction of the new dam. They wanted a larger demonstration project to show that they really could take the reactive aggregates, combine them with the mitigation option with the recommendation of a high percentage of fly ash to really control the reaction. So in 2008, I went out and was part of the construction team for casting probably the largest outdoor exposure site in the world. These blocks measure 10 by 10 by 10 feet, and there are 5 of them. So if you look from a distance, we're actually looking down. The kind of blue you see is actually the water of the river flowing through the dam. The dam would be kind of behind us to this side. And there are 5 blocks there. There's a control block, so no mitigation options at all. Then there's a 30, a 40, and a 50% fly ash replacement in each one of 3 additional blocks. There's also a 5th block that has a 50% fly ash replacement that's from a deposit of fly ash that's been specifically reserved for this dam. So they anticipate using the fly ash that's coming from the coal-burning power plant that's very close to this dam. But they've had the foresight that if the fly ash is no longer available, or if that coal plant closes down, they've actually reserved a section of fly ash set aside specifically to have enough to reconstruct this entire dam project in about 15 years. So it's a pretty extensive study that's gone on to actually make sure that we're not going to have any problems with ASR. So we're monitoring this now. The control block has already started to expand, started to show some signs of cracking. And we're going to be monitoring this, obviously, right up until the point of construction. So I do have a few more slides, but I think what I'll do is I'll just end it here. I can give those slides to either Hal or Chris, and certainly feel free to post those for everybody in the class. There's a little bit more information at the end. But we'll open it up to questions, because I know you guys probably have some questions and have to ask some questions.
Yeah, and just as a reminder, if you ask a question, to use the microphone. And for those people that are watching on the web, my laptop failed to connect, so I can't read your question. So, so sorry about that. So.
Okay, I think you were first.
So I'm not a chemist, but it would seem like maybe you could add the lithium into the concrete before it's cured rather than trying to apply it from the surface afterward. Would that be effective at all? Would that compromise the concrete?
Yeah, that's a great question. I didn't have time to get into that because we really wanted to focus on what you can do in hardened concrete. You can use lithium mostly effectively in fresh concrete. Lithium has been used in concrete since about the 1950s to control ASR. It was about 10 years after ASR was first discovered. What we've kind of come across though in the past 10 years is that the dosage rate of lithium has typically been set at a 0.74 molar ratio for fresh concrete. That's a ratio of lithium to sodium plus potassium. But what we found is that that amount actually varies depending on the reactivity of the aggregate. So you can use it effectively in fresh concrete. You just have to use the right test to know how much lithium you need to control the reactivity of a certain aggregate. So it's a very viable option. But we have a lot of structures in the field that are already undergoing ASR. We're trying to find mitigation options for, which is why we're interested in potentially trying to drive the lithium into the structure. I think you had a question?
Yeah, just more on the plastic side, though. What about using air entrainment?
Air entrainment is not an effective way to provide enough accommodation for the gel. There's so much gel that's formed. It may provide you a little bit of reduction in expansion, but once those air voids fill up with gel, then they can, one, no longer provide protection for freeze-thaw attack, and you're going to end up getting ASR going on anyway. So they can provide you a little bit of protection, but it's not an effective mitigation means for ASR.
How about in a non-freeze-thaw cycle environment?
Still not enough. There's so much gel that's formed. Maybe with a very low reactivity aggregate in a climate where you don't have moisture and you've got low alkali content in your cement, that might work, but it's not something I would hang my hat on at all. Yeah, I think in the back, you're next.
How cost effective is it with pushing the lithium into the concrete like that? It seemed like it would be a really expensive way to treat these structures. And if you compared that with the admix on these new structures, if you've looked into any kind of a cost assessment?
It's certainly much more cost effective to prevent ASR from happening in the first place. Using supplementary cementing materials like fly ash and slag, and even in some cases, depending on availability, can reduce the cost of the concrete. So by putting in supplementary cementing materials like slag and fly ash, you're typically not affecting the concrete cost by more than about 5 to 10%. When you start putting in silica fume, it's one of the more expensive pozzolans, but because you put it in much lower dosage levels, it's also not a significant impact on the cost. Putting lithium nitrate into fresh concrete is substantially more expensive than using supplementary cementing materials, but if you don't have those methods available locally, then lithium nitrate may be a very viable option. When you start talking about repair, the columns that were done in Houston, there was electrochemical injection done on 2 of them. That system was set up for a period of about 4 to 5 weeks, and that cost about $300,000 for those 2 columns, and it didn't work. So certainly it's more cost effective to find a mitigation strategy for something you can do to the existing structure rather than tearing it out and replacing it. But the most cost-effective means is to do something early on. Know you're going to have a problem and mitigate for it when the concrete's in the fresh state. Yeah.
You probably have already addressed this, but I was wondering about the length of time for the exposure test, and also whether or not it would be possible or feasible to shorten that time.
I didn't address it just in the interest of time, but it's a great question. Our most accelerated lab test is a 14-day test right now. It's incredibly aggressive. The concrete goes into 1 normal sodium hydroxide at 80 degrees Celsius. But there are a lot of drawbacks to the test. One, it's overly aggressive, so it tends to fail a lot of aggregates that may pass in the field, meaning they're not going to have ASR problems. You also end up with the risk in that test of having a false positive. So it tells you that, or a false negative rather, where it tells you that the aggregate isn't going to be reactive, but it actually is in the field. The next step up from that is a 1-year-long test. It's the most reliable test that we have, but if you can find a contractor that wants to run a 1-year test, please send them my way. I'm happy to do that testing. The big take back from that is that the U.S. is kind of behind Canada and behind Europe, in my personal opinion, in terms of how we characterize aggregate reactivity. Quarries in Canada typically are running these longer-term 1-year tests all the time, and they're benchmarking constantly with the 2-week rapid test. So they can easily go back and compare, okay, we've gotten into a seam of aggregate that's very different. We can go back to our historical records and see, okay, we know the mineralogy of it, we know what the expansion is in this rapid test, and they can benchmark it to one of their longer-term tests. Then when you get into exposure site testing, it really depends on the environment. So we may pick up reactivity in as short as 1 to 3 years in Texas, whereas in a climate, here where we have a lot of moisture, but we have a much cooler climate, it may take 3 to 5 years. And in parts of Canada, it may be a 5 to 10 year process. So no one's really starting to make that link yet, and we're trying to do that so that we can get what the best test method is to use in the lab. Yeah. I don't know, maybe in the back and then here.
Are there health risks or other environmental impacts when spraying the silane coatings?
That's a great question. The honest answer is I don't know what they are for silane. For the silane applications, it's typically a very near-surface application, and it's in a very dilute concentration in either a water-based solution or an alcohol-based solution. We've also been concerned about lithium nitrate because if you're applying it to a pavement, you typically get a lot of runoff that can run off into the shoulders of the roads. And we've repeatedly asked the manufacturer for that type of information, and they're unwilling to provide it. So I think that's a concern also. Yeah, I think you were next.
Then I kind of had a similar question. If
Sure.
you're looking at these applications from a sustainability standpoint, I guess sourcing lithium or the, like the fiber reinforced polymers, what's the relative scale of those, and then versus the larger picture of saving the concrete structure?
Well, that's where getting into a detailed life cycle analysis is something that is really important to do, depending on what the repair is. Certainly, the most effective is to have the right detection methods in place early on, so that you make sure you're putting in the right materials at the beginning when the concrete's in its fresh state to make sure you don't have any of these problems in the long term. It does get very complicated when you get into dealing with structures that have this going on and making that kind of benefit. I think the tough part is right now we don't know enough about the long-term effectiveness of lithium if we can actually drive it in and not cause the reaction to occur. And we don't know enough about carbon fiber reinforced polymers yet either for their long-term durability. Another professor at Oregon State, Chris Higgins, is working on a project looking at durability specifically of these carbon fiber reinforced polymers. I think he's going to be able to provide us a lot more information so we can start to do some of that life cycle analysis. But it's not something that the industry has typically done, and it's a place where we need to go. So I think it's a good point. Maybe back and then front.
You mentioned crack injection as a form of mitigation.
Yeah.
Now, does that actually slow down the ASR, or does it just fill in the cracks so that water and other minerals can't get in there?
Yeah, it's a good question. And the answer, I guess, is it depends. Certainly, initially, it can slow down the reaction because it's limiting how much moisture can come in. But if you're not doing something to actively limit the moisture just coming into the concrete due to its own permeability, it's really only a stopgap. It's really only going to buy you some time. So you need to combine that type of a method with a way to try and dry the structure out also. Yeah.
Do the dry states like Nevada and Utah, do they not have as much of a problem, I'm guessing?
They typically don't have as much of a problem. What unfortunately works to their detriment is that they have highly reactive aggregates. So in a lot of, not the entire state, but in certain places they have very highly reactive aggregates. Arizona is one of the places that has one of the most highly reactive aggregates that we know of. So even a small amount of moisture for those structures can be enough to drive the reaction. Two in the back row.
I was wondering, like in the Texas example, when you guys drilled in and that caused more sodium and potassium to try and get lithium in, have you guys ever looked into trying to say, pre-treat the aggregate with lithium or the rebar so it's already in there so you're not having to drill in?
Yeah, there have been studies that have looked at, I don't think any studies that I know of that have looked at coating the rebar, other than having an epoxy coating on the rebar. But there have been a lot of studies that have looked at soaking the aggregates or spraying the aggregates with lithium initially. It seems to provide you some level of protection, but it seems to be better to have it mixed in with the fresh concrete so that you have it distributed in the paste and in the aggregate as well. So it's a good idea.
This is something you touched on earlier, but I'm just wondering what are if you know the practical limits of transporting in aggregates with low reactivity into construction areas where the local aggregates have a higher reactivity?
The short answer is it's basically impractical. Yeah, I mean, if you don't, that's one of the things that keeps concrete so cheap. That's why it's the most used building material, because it's just so inexpensive because you use your locally available materials. So the second you start getting beyond about a 40 to 50 mile transport radius for bringing in aggregate, the cost just skyrockets because it's it's the densest part of your mix, and it's the part that's helping keep your costs down. The Portland cement is the most expensive part of the mix. So anything you can do to limit how much Portland is in and how far you're having to transport that is really going to impact your economy on that side.
All right. Before we thank Jason for the interesting seminar today, make the announcement that, of course, next week is Thanksgiving, so the university's closed on Friday, so no seminar. You can come, but we won't be here. And then on the following Friday, Jennifer Dill will be giving a talk from Spokes to Sprockets, a history of women and the bicycle. So with that, thanks, Jason, for your presentation today.
Thank you. Thanks very much.